Let me stay for a few minutes on a technical point that may bother you, maybe not, but just in case it does, I'm going to address it. If you go back through the example I just showed you, you'll notice that at some point we assumed that the square root of cosine squared of theta was cosine theta. However, this is sort of a junior high school kind of assumption, because we know now that in general, if I'm computing the square root of cosine squared theta, that's really the absolute value of cosine theta, right? So why can I make the assumption that in fact cosine theta is positive, and therefore I can ignore the absolute value, which is what I did in the computation of that integral? Shouldn't I leave those absolute values in there? All right, let's see why I can in fact make that assumption. Okay, in our case, notice that our integral is the square root of 4 minus 9x squared, which means that in order for the whole thing to even be defined, we need 4 minus 9x squared to be greater than or equal to 0. That implies that we need 3x over 2 to be between negative 1 and 1. If you're a little bit lost about how I made that jump, this is an inequality, and you may want to maybe pause and prove on your own that in fact that is the case. But again, once you do that with your algebra skills, you'll realize that in fact, in order for anything we're doing to be valid, 3x over 2 has to be between negative 1 and 1. Now, on the other hand, when we set 3x over 2 to be sine theta, we were really assuming that the relationship we wanted had to be invertible. So in other words, we started from x, we changed to theta, and we needed to go back to x. So we wanted that relationship to be invertible. What that means is that in setting that equality, we were restricting the domain of theta to just values between negative pi over 2 to pi over 2, which is the interval over which the sine function is invertible. Alright, but if theta is between negative pi over 2 and pi over 2, how is the cosine of theta? Half a second to think about it. Yes, the cosine of theta has to be positive. Okay, so yes, we're fine, great. We don't have to worry about it. Just be happy. This is again a very small technical point that I brought up because some books do, and you may want to think about that yourself, because it may look like I'm contradicting what I've been saying earlier about the square root of x squared being the absolute value of x. In this case, it looked like I was ignoring that, but no, I'm not. Because of the way we have set up the whole change of variable, it turns out that cosine theta is actually greater than or equal to 0. A similar kind of problem will happen also in the other situations where we're going to use the other identities to solve similar integrals. Okay, and so from now on, you don't have to worry about it. So there are other cases. Remember at the beginning I showed you 3 Pythagorean identities, 3 corresponding forms involving the square root of a sum or difference of 2 pieces, one of which was a constant, the other one was the square of a function. Okay, so how are we going to deal with the other cases? Well, they're done exactly in the same method. The only thing that is going to change is we're going to use different functions and we're going to use different identities. And so we're going to have to choose which identity we're going to choose where, but again, that's going to be pretty obvious in the sense that we have to choose the identity which is of the proper form. We're going to see that in class repeatedly. Also, when whatever method we use, at the end we're going to end up with an antiderivative in terms of theta. We'll have to go back to x, and in each of those cases it's a good idea to use the right triangle model. So you set up your triangle, you pick your angle theta, according to it you figure out the 3 sides of the triangle, and then from that you figure out all the other pieces that you need, and believe me, it's always going to work out. So the one thing to remember is that again the image you want to look at is something like this. Now if you draw your triangle in the other way around, or if you label as theta the other angle, that's fine as long as the sides are then labeled correspondingly. Okay? So you want to try with different approaches and see which one works best for you. Okay. Now the integration steps may be different. I showed you particularly a basic example. In other situations there may be other pieces besides the square root in question, and therefore we'll have to see how those pieces combine and so on. But again, the fundamental theorem of cooked up exercises will work, and so the integrals will always be done in such a way that things will cancel nicely, will combine nicely, and in the end you will be able to compute the integral. Now, the other thing is that if you remember, hyperbolic functions have identities which are fairly close, fairly similar to the ones for trig functions. And some people like to use those those hyperbolic identities with the same method in order to integrate certain square roots. Again, we're going to see a couple of examples of that. You may want to look some more in the book. You may want to decide on your own whether you prefer to use trig substitution or hyperbolic substitutions. They both are valid as long as they're implemented correctly, and so you can be free to use whichever method you want. Finally, as I've said before, this is an integration method. Nothing will beat practice. So you have to practice, practice, practice in order to understand all the many variations, all the many different things that can happen, and also to recognize when this method will not work, or even the situation where the method does work, but there is an easier way and we don't really need to go through all this rigmarole of this method, which, as you can see, is probably the most complicated method we've seen so far. So practice, 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 ask questions, and don't give up.